Welcome to gravimetric analysis. So what we're going to try to do today is we have an unknown solution here of a copper chloride solution. And copper, if you don't already know, comes in two different varieties. Copper either comes as the +2 ion, which is the more common of them, or the +1 ion here. And right now, we don't know which one this solution is. It's either copper with a +2 or copper with a +1 that's there. And right now, I'm not telling you which one of these guys it is. But we can figure it out using chemistry. So what we are going to do is we are going to take some copper solution and we are going to react it with something that will cause a precipitate, which is an insoluble substance. And then we are going to collect and weigh that precipitate, do some math, and then figure out which one of these guys it is. So the substance that we have chosen to react it with is the carbonate ion. We're going to use some sodium carbonate, not that we care about the sodium because it's going to be a spectator, in the same way that the chloride is going to be a spectator, because if the chloride and the sodium get together, they're just going to make salt, and in water that dissolves, so we don't care about them for right now. So what we're going to do is we are going to react these guys here. It's either going to be him or him, and we're going to react it with the carbonate ion to create a precipitate. So take a moment and write the net ionic equations for the reaction of the copper +2 ion with carbonate, and then the reaction of the copper +1 ion with carbonate. All right, if you've unpaused at this point, here are your reactions. The first one here is the copper +2 reacting with the carbonate, which is a -2, going together to make the copper carbonate. Again, we are ignoring the chloride and the sodium because they are spectator ions. Now the copper +1 is going to be the same thing, except that I'm going to need 2 of the copper +1s to react with the carbonate -2 in order to create this copper carbonate here. Because again, you need as many positives as you have negatives, and if this guy is only a +1, then I'm going to need 2 of those. Now, that's where the difference comes in as far as how much of the precipitate we are going to be able to collect at the end. So what's important here is that we are going to start with the easy one. What's important here is that we know how much of each of the solution we are going to need to add to ensure that we have quality amounts. So let's start and make sure that the copper ion that we have is the limiting reagent. We are going to use 50 milliliters of the 0.1 molar solution that we have there. Now, in order to figure out how many moles this is, we were going to need to take the 50 milliliters and turn it into liters. So that's going to be 0.050 liters. And then if we use our molarity equation, that molarity is equal to moles per liter, or that moles is equal to the molarity times the liters, and we multiply these two guys here together, we get 0.1 molarity times the 0.05 liters here, and we end up with 0.005 moles. Now, using our stoichiometry, and I know we haven't really gotten to that yet, but we're going to do some simple proportions here. Because there's a 1 in front of here and there's a 1 in front of here, we're going to need as many of these guys here as we have these guys over here. So we're also going to need 0.005 moles over here. But we kept things simple. Remember that I made the sodium carbonate solution a 0.1 molarity in the same that I made the copper solution a 0.1 molarity. So again, this guy here is the same concentration as this guy is here. So just some little logic math will tell you that if we need the same amount of these guys, and this is also 0.1 molarity, then I would also need 0.050 liters there. So I would need the same amount. So I'm going to need 50 milliliters of this guy, and I'm going to need 50 milliliters of this guy to make sure that I have enough to get proper precipitation in order to create my copper carbonate over here. So if it's the copper +2, then I would need 50 and 50 that's there. But what if it's not the copper +2? What if it's in fact the copper +1? Well, let's use the same kind of logic. If I take 50 milliliters of this guy at 0.1 molarity, Then I'm going to change that into liters. I'm going to call that 0.050 liters. That's there. Write that a little bit better. That's going to be 0.005 moles. All right. Please recognize that for every 2 of these, I only need 1 of those guys. So I need half as much of the carbonate over here as I needed of the copper, because I need twice as much copper as I need of the carbonate, or I need half as much carbonate. So I really only need 0.0025 moles here, and because it's 0.1 molarity, then I would need 0.025 liters, which would be 25 milliliters. So when going to do this experiment, I either need to add, for 50 milliliters of my unknown copper solution that I have here, I either need to add 50 or I need to add 25, but I don't know which it is, so to be safe, I need to make sure that I add the 50 that's there. But because if I add too much, it's really not going to do anything because there's not going to be enough copper to react with it, I'm going to go ahead and I am going to add excess of this, because this is my limiting reagent. So basically what it's going to come down to, guys, is that I'm going to measure out 50 milliliters of my copper solution, and I'm going to measure out at least 50 milliliters of my carbonate solution. That will ensure that regardless of whether or not it is the copper +2 or the copper +1 that we have here, I will have enough carbonate to react with. So we have now done our measuring. I have gone through and I have gotten us right at 50 milliliters of 0.1 molarities of our unknown copper solution. And then I went ahead and got some excess of the 0.1 molarity of the carbonate. I didn't want to go too crazy, so I made it about 55 or so, if you can see that there. So this guy here, I have excess. I've got too much of him to make sure that all of this guy here reacts with each other. So now all you have to do is you have to take each of these guys and you have to react them. So I'm going to go ahead and pour him into a beaker, and I'm going to pour him into a beaker, and watch what happens, because again, take a moment and predict what's this going to look like when it's done. You're creating an insoluble precipitate with this, and so what's it going to look like? So here I go. Watch what there. Oh, look at that. It turned cloudy. And now I'm going to give that guy a stir, 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 stir. Now, we only want the cloudiness. We don't want the water. So what we're now going to have to do is we are going to have to filter this guy. If you are just qualitatively filtering, you can skip this first part, but if you are quantitatively filtering, then you need to know what this filter paper weighs. So first of all, let's fold this guy. How do you fold him? You take him and you fold him in half to make a semicircle, and then you fold him in half again to make a pie wedge, like so. That's going to fit much easier on the scale this way. Now you're going to come over here, and we need to know how much this guy weighs. So I'm going to go ahead and hit tare. Make sure that that guy is zeroed out, and then I'm going to put him on there. And this says he weighs about 1.7 grams. Now in pencil, and again only in pencil because the pencil won't rub off, make sure that you write down 1.7 grams on your filter paper so that you don't forget. Because if you forget, you're kind of hosed. All right? So now what we're going to do is we're going to take this, and you'll notice that there are now 4 layers here. 1, 2, 3, 4 different sheets of paper because I folded it and folded it again. What you're going to do is you're going to put your finger in there and make 3 in 1. It doesn't matter which side. You can go 3 in 1 this way, or if you want, you can go 3 in 1 this way. Put your finger in there like so. It really doesn't matter as long as there's 3 layers on one and 1 layer on the other. And then this whole thing goes into a funnel like so. And now what we're going to do is we are going to pour this here through our filter paper here to collect all of the precipitate. So once again, you want to set this up so that it's 3 in 1. It doesn't really matter which way you do it as long as it's 3 in 1. Go ahead and shove that guy down in there, and then take your precipitate and pour it right in to that one layer that's there. Put a little bit in, and it will start to drip through. And you can add some more and more and more, but what you can't do is you can't go above the white filter, because if you do, what will happen is some of that precipitate can then sneak through in between the filter paper and the filter itself and go down into our beaker down here. And we want to catch all of that. The other thing that you don't want to do is start poking at it, because if you start poking at it, this is just made of paper, and the paper will break. And if you break the paper, then again, everything will come on through. Now, please note that the color that's coming through here is not blue. All of the blue is staying up here. Take a moment and think about that. Pause the video. Why would that be? Why is the blue not coming through down here? Why is the blue staying up here? Well, if you've unpaused, the answer is because the copper ions were the limiting reagent. These were the ones that we had in excess. The copper were the ones that limited. And because the coppers were limiting, there were not extra of those. All of those copper ions are now trapped within our precipitate of the copper carbonate, which is why they are not coming through down here. So the filter is catching the precipitate and letting everything else through. After a while, after it's gone down a little bit, you can be sure to add a little bit more. But again, you don't want to add so much that it goes over the edge of that, because if it goes over the edge, you're in trouble. This is the boring part. This is the waiting around for this to drip through part. What we now have is a filter that has really done a pretty good job of getting all of the precipitate there. But you can tell it's still kind of wet in there. We got to get rid of all of that water. And again, take a look at what came through down at the bottom. This is what was caught down below. Almost no blue down below. So up here is just the precipitate. That water is in there, and we've got to get that out of there in order to get an accurate reading of things. Now, we could just let it sit and evaporate, but it would be much faster if we were to give it a little extra help. So what I've done now is I've just gotten it out of there, and I have put it on a watch glass there, and that is going to let it evaporate even better. Because it will be exposed to more air. Of course, an even better way to help it along is by cooking it a little bit. So we've got an oven here that we've got on low. We're going to open this guy up, and we're going to take our wet precipitate, and we are going to put it in there, and this is just going to gently heat this guy up and gently heat the water off. We don't want to burn it, we don't want to roast it, we don't want to actually cook it. All we want to do is heat it up to accelerate the water removal process. Okay, so what I'm going to do now is I am going to let that guy cook for a while and pull him out. And when I've pulled him out of the oven, he looks a lot different than when he went in. But I don't know if he's done yet or not. So the only way I can tell to see if he is done yet or not is to weigh him and then put him back in and see if after a little bit more time that weight actually goes down. So right now he's at about 3.1 grams of the filter paper with the precipitate that is caught on top. But what I'm going to do now is I'm going to put him back into the oven and let him cook for a little bit more. So I've pulled him out of the oven, and check him out. The weight has gone down, so clearly he was not yet done. So it's gone down to 2.5. Got to put him back in. So after a few minutes, look, it's gone down even more. It's 2.3 grams now instead of 2.5 grams. So maybe there's still some moisture in there that needs to be heated off. So back into the oven he goes again. Now this guy is finally done. The weight on this guy has not changed. After successive cookings, the weight is remaining the same at 2.3 grams. So that's really kind of the only way that you could tell that all of that moisture has been heated off of there, is to heat it repeatedly and repeatedly until the mass of it does not change. So it's hard to believe from just these three numbers we're going to be able to figure out what the formula is, but you can if you know how to do it. So first of all, we know that the mass of the filter paper alone was 1.7 grams. That's going to be important. We know that the mass of the filter paper with the precipitate when we were done was 2.3 grams, and we know that we used we used exactly 50 milliliters of 0.1 molar copper. The carbonate we're going to be able to deduce from our math. So the first thing that we need to do is to figure out how much precipitate was actually there. So how much of the precipitate was actually collected? Well, if it was 2.3 grams of the filter paper with the precipitate, if we just subtract out the filter paper, we should get the mass of just the precipitate that is there. So the mass of the precipitate collected is going to be 2.3 grams of the paper plus the precipitate minus the 1.7 grams of the paper, and that should get us then 0.60 grams of the copper carbonate, and we don't know their formulas, precipitate. All right. Now, we know that of the 0.6 grams, some of it is copper and some of it is carbonate. Our job, again, is to figure out the moles here and the moles here to figure out, is it a 1-to-1 ratio or is it a 2-to-1 ratio? Well, we need to know both of them, but the nice thing is that we have the whole thing together, and if we know one of them, then we can know the other one by logic. So which one do we know? Well, we know that we used 50 milliliters of 0.1 molarity of the copper ions. Remember that from up here? The copper ions, we used 50 milliliters of 0.1 molarity of those guys. That was our limiting reagent. So what we're going to do is we're going to use the equation molarity is equal to moles over liter, or moles is equal to the molarity times the liters. So all I need to know is the molarity in the liters, and I'm set. Well, I've got the molarity, that's 0.1. And I need to know the liters. Well, I have the liters, I just have them in milliliters. So that's easy enough to fix. I'm just going to change that to stop it. 0.05 liters that's there. So it's 0.1 molarity times 0.05 liters that is there. And you end up then overall with 0.005 moles of copper. So when we go down here, we know what we're trying to do is we're trying to get copper X and carbonate Y. We just figured out what the X is. We know that the X is the 0.005 of the copper because we know we started with that. So I'm going to go ahead and write that one in. I know that the copper is 0.005 moles. Now all I need to do is figure out how many moles of carbonate were there, and I am in good shape. So how are we going to do that? Well, what do we know? We know that there are 0.6 grams of the copper and the carbonate, and we know how much copper is there. So if we just subtract out how much copper is there, that'll tell us how much carbonate is there. So what do we know? We know that there are 0.005 moles of the copper ions. Well, if I know moles, I know grams. All I have to do is use the periodic table and multiply. So the mass of the copper ions is going to be 0.005 moles times its molar mass from the periodic table, and if you look that up, it's 63.5 grams per mole. So if you do a little mathification on this, you end up with 0.3175 grams of the copper. All right, so now guys, check it out. We know that overall there was 0.6 grams of copper and carbonate, And we know now that there are 0.3175 grams of the copper. So whatever is left over of our 0.6 that is here, that is not this number, should be the carbonate that's there. So all we have to do is subtractify those guys. So this one is going to be 0.60 grams of my copper carbonate, X and Y, minus my 0.3175 grams of my copper, is going to end me with 0.2825 grams of my carbonate ions that were added through the precipitation. Well, if I know grams, I know moles. All I have to do is turn those grams into moles. So our last one here, the moles of the carbonate ions, 0.2825 grams of carbonate ions. All I have to do is divide that by its molar mass. And remember, you're talking about CO3. If you go to the periodic table and add those up, you get 12, 16, 16, and 16, so that's 60. So again, 12 for the carbon and 3 oxygens, each at 16. So this is going to be 1 mole per 60 grams. And if you do the math on that, that turns out to be 0.0047 moles or so. So that is now my number that goes here, 0.0047. So just by looking at them, can you tell, is this a 1-to-1 or a 2-to-1 ratio? Are these numbers almost exactly the same? Or is this number here about twice what this number is here? Well, let's just do a little rounding here. This is 005. This is 0047. Even if I rounded that, that would be about 0.005. They're about the same. So again, if I went and did all of the math on that, then what I would do is I would divide by the smaller of the two numbers, 0.47 and 0.0047, and what you basically end up with then is you end up with a copper 1.06 to carbonate 1 ratio. Look, it's a 1-to-1 ratio. The copper and the carbonate is 1-to-1. So that means then that the copper must be the +2 charge to balance out with the carbonate that is the -2 charge, because it is a 1-to-1 ratio.